We now consider the flow between two circular cylinders. So it's just the same as considering a flow between two plates. But if we keep the plates fixed, let's say in horizontal direction, then their analogy in the rotating cylinders is of the same type, that the two cylinders are moving and the fluid is taking place between the annulus between the space created by the boundaries of the two cylinders. So I think we can show here the geometry that there is a cylinder here and then there is another cylinder here. So this is solid and this is the space in which the fluid is moving. So this it's cylindrical in nature, remember, and the fluid is moving in the space created by the two cylinders. Now we can keep the geometry or the fluid flow situation triggered by this cylindrical motion in such a way that one cylinder is kept fixed and the other is allowed to rotate. Both the cylinders are allowed to rotate. So then there will be a relative viscosity action and the fluid flow will be generated, triggered by viscous action. So this is described here in mathematical terms, that R2 is greater than 1. It means that the radius of the outer cylinder is R2 and the radius of the inner cylinder is R1. And the corresponding angular velocities are omega 1 and omega 2 respectively. Since it is cylindrical geometry, so as I have mentioned somewhere, the cylindrical coordinates will be chosen, maybe r theta z or r phi z. So this reflects to the angle where and r is along the radius and z is along the axis. So this is even described here. Because of the symmetry, the equations of motion will be simplified to this version. Now remember, we have to write down the Navier-Stokes equation by converting the rectangular coordinates into cylindrical coordinates, and the cylindrical coordinates chosen are r, phi, z. From continuity equation, we will obtain this result. The other component vanishes. So since the partial derivative with respect to phi vanish, it is obvious that v does not depend on phi. V depends on r, the radius. And therefore, if v is depending on radius, we make use of this result and try to see how the momentum equation in the x, y, z direction or correspondingly in cylindrical coordinates r, phi and z direction, how they change or what values they give. So we obtain from the first equation that dp by dr is equal to this value, and from another equation, the radial direction, we obtain that the velocity vector v will give us this result. As a standard procedure, since here this is all depending on r, we shall integrate it twice because there is a second derivative. This was a partial derivative, but since it's only dependent on r, we will write it as a total derivative. We integrate it, and since the differential equation is of order 2, in the solution, two arbitrary constants A and B are occurring. To determine the values of A and B, in fact, we have to substitute, we can find out with this value, we can obtain the value of P that we have calculated early in terms of this equation that we have just obtained here. So we can find out the value of P. So now we know, if we want to know how the pressure would look like at a certain point R, it's given by this value. A, B, and C are constants of integration. The constants of integration can be determined by applying the no-slip conditions in the case which are written down here. The no-slip condition again is referring to the boundaries where, due to viscosity, the fluid will not be flowing and will be sticking to the wall. So that means fluid will be moving with the same angular velocity with which the cylinder is moving. Substituting them, we obtain the values of the unknown constants A and B, and from this, the frictional stress of the inner cylinder is obtained. So these are simpler equations, the components. We just have to substitute the relative values that are required there. And similarly, the force acting on the unit length of the cylinder will be of this values, where R1, R2 are radii of the two cylinders, omega 1 and omega 2 is the angular velocities of the two cylinders respectively. And similarly, if we want to calculate the moment, then the moment of the force will be equal to this one. This is the results that we obtain from motion that is generated by two coaxial circular cylinders.